Alright guys, so today I'm going to try and develop the idea of a Taylor series. Okay, this just comes from a power series like we have here. So here f of x is the sum of this power series. It is centered at x equals a, and this c sub n represents the coefficients of every single term of this power series. So we have a sequence of coefficients going out, all right? And so what do these coefficients have to actually be equal to? Well, first, we should note that f of a, that is, if you plug a into this particular f of x, all of these x minus a's are going to disappear because they're going to be 0 when you plug in a. So it means all the terms are going to disappear, and you're just going to be left with c sub 0. Okay, so c sub 0 has to be equal to the y value at a. Second, consider f prime of x. Well, what is f prime of x? It's the derivative. So the derivative of c sub 0 is going to be 0 because that's just a constant. That's f of a. The derivative of the next term is just going to be c sub 1. The derivative of the next term is 2 times c sub 2, x minus a to the first. That's just the power rule. Next one is going to be 3 times c sub 3, x minus a squared, and so on. And so using the same kind of idea from before, from the first set, f prime of a is just going to be equal to c sub 1. All right, so we're defining these things using this derivative. Let's take a look at the second derivative, f double prime of x. Well, if we take the derivative of f prime, we're going to get 2c sub 2 plus 3 times 2 c sub 3 x minus a to the first plus 4 times 3 x minus a squared, and so on. And f double prime of a is going to be equal to 2 c sub 2. Or we could say c sub 2 has to be equal to f double prime of a over 2. So, having this pattern and seeing, okay, if we went to did the third derivative, this is going to be equal to f triple prime of a. And then 4 times 3 times 2 is going to be the fourth coefficient, c sub a, divided, the fourth derivative divided by 4 times 3. So it appears to me that the nth coefficient is going to be equal to the nth derivative at a divided by n factorial. Either 3 times 2 or 3 times 2 times 1 or so on. So that f of x is going to be equal to the sum where our coefficients are the nth derivative at a divided by n factorial times x minus a to the nth power. All right? This going to infinity is what we refer to as a Taylor series. All right. If we stop this at some value n, if we like only do a partial sum, we call it a Taylor polynomial. So a Taylor polynomial would be the sum to the nth. That would be the nth degree Taylor polynomial. All right. Just about Taylor polynomials, a linear approximation is really just a first degree Taylor polynomial, right? A linear approximation in general was like f of x is equal to f of a plus f prime of a, x minus a to the first, right? If we did like a quadratic approximation, that would be f prime of a, I'm sorry, that's f of a, not f prime of a, excuse me. So that's f of a plus f prime of a, x minus a, plus f double prime of a over 2 x minus a squared, and so on. So that would be kind of a quadratic approximation. Okay, so this is what a Taylor series and a Taylor polynomial is. A Maclaurin is just a special case. Sometimes we'll see the name Maclaurin. So a Maclaurin series is a Taylor series centered at 0. Okay, so I'm going to do an example right here. All right, let's write the Maclaurin series for, let's say, e to the x. Okay, so to do this, we've got to come up with a couple of derivatives here, right? So we've got to think of what is f of 0, right? Because that means we're going to center at x equals 0. That's our a value. So f of 0 is 1. F prime of 0, well, that's just going to be equal to 1. And f double prime of 0 is going to be equal to 1, and so on, because the derivative of e to the x is itself. So that means our particular f of x is going to be 1 plus 1 over 1 factorial x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, and so on and so forth. We could actually write this out as n equals 0 to infinity 1 over n factorial x to the n is going to be its Maclaurin series. We can use, let's say, use the first no, we're not going to do that right now. We can find the interval and radius of convergence of this series by, again, applying the ratio test. So take the limit as n goes to infinity of 1 over n plus 1 factorial x to the n plus 1 all over 1 over n factorial x to the n. If we simplify that, we're going to get x over n plus 1 less than 0, or less than 1 rather. And this is going to hold true for anything, because what's inside here is actually going to 0, which is less than 1. So this really is for all x. That is, the radius of convergence, or the radius, right, is infinite. Right? Our interval of convergence goes from negative infinity to positive infinity, and we can go ahead and graph and kind of show that would be the case. If you go ahead and graph this in Desmos, along with graphing e to the x, the more and more terms that you add on, it'll continue to converge, and it'll get wider and wider and wider as it goes through. Okay? So that is the Maclaurin series for e to the x. I'm going to do one more series to show you guys how to find a Maclaurin series. This time, we're going to find the Maclaurin series for sine of x. All right, Maclaurin series for sine of x. Let me just add another page on here. Okay, Maclaurin. For sine of x. So, first of all, f of 0, 0. F prime of x is equal to cosine of x. Of course, f prime of 0 is equal to 1. F double prime is negative sine of x. F double prime of 0 is 0. F triple time prime of x is negative cosine of x. This is going to be negative 1. The fourth derivative is back to sine of x. So this is 0. And I think we can see it's going to go, 0, 1, 0, negative 1, 0, 1, 0, negative 1, and so on and so forth. And so it looks like the series for this is 0 plus 1 over 1 factorial x plus 0 x squared over 2 factorial minus 1 over 3 factorial x cubed. Next one would be, where do we go? That was the third. Now we're back at 0, so 0 over 4 factorial x to the fourth. The next one is going to be plus 1 over 5 factorial x to the fifth, and so on. So if I get rid of the zeros in here, the terms that are not supposed to be here, it looks like it's 1 over 1 factorial x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the seventh, and so on. And so we only have odd degree terms, and we have this alternating series, which is kind of expected because we know sine of x is an odd function. So that is, f of negative x has to be equal to negative f of x. Well, that's why we don't have any even exponents in here on our x's. It's all odd exponents because it's got to be an odd function. All right? I'll leave it up to you guys to find the radius of convergence here. This here is going to be n equals 0 to infinity. Looks like it's going to be negative 1 to the nth power all over, we're going to do 2n plus 1 factorial, because it's got to be odd numbers, 2n plus 1 factorial x to the 2n plus 1 power. So that is my general term for this. You can plug in 0 and see that it works, and then plug in 1, works, and so on. So this is the Maclaurin series for that. Please try and find the interval of convergence and radius of convergence for this. I'm also going to assign you guys to find a couple more Maclaurin series and put that, kind of upload, show your work, and put it in a document on Google Form, all right? All right, thanks for watching.